Fits. We love it. We published a paper called "The Future of," or Lessons Learned from Fits, and there's a lot of nice things to say about fits in it. And actually, I'm not kidding. There's a reason that fits is sticking around, and you actually, I think anybody who's going to try and move on to the next thing has to understand why fits has been so sticky in our community and why it's still the dominant format. So here's one of the great reasons. The inspection is really easy. You can open it up in a text editor and you can see what's going on. You can make minor changes to it this way and they actually work. Now it seems like a minor point. We're all used to getting the library that reads the API for the format. But this is really easy and it's really important and it's not something that a lot of other formats can do. On the other hand, it's also very efficient because it stores the binary data as binary data. So if you have a really large file that you can't fit into RAM, you can just mem map it. Even if you are going to load it into RAM, it's really easy. You're just copying the data in. Makes it easy to do partial reads. You know, you have a big data cube. You can easily just read one frame at a time, assuming it's ordered correctly. And it's pretty simple. You could, sit down with someone in 15 minutes and kind of explain how the file format works, except when it isn't simple. And there's these little surprising details about it, but I think on the whole you can say that it's a pretty simple format. And so I think anything you're going to do to try and kill fits, you have to also do these things, or people will think it's a regression, right? There's some ways in which we really don't like fits, and of course this is our motivator. The comprehension, you have these 8-character keywords. What does that mean? Who in this room can tell me? The structure, everything's very flat. You have a flat list of key value pairs, you have a flat list of HDUs. It's very difficult to say this thing is related to this other thing, this thing is owned by this other thing, this thing depends on this other thing. You can't really do that in fits without building a lot of additional complexity. And evolution is really poor. There's this statement, once it's fits, it's always fits. There's one version of fits. We're not allowed to say this is the new version of fits. And so rather than saying, oh, this is a new fits file and I can do these new things, libraries have to kind of guess, and they still have to remain backward compatible with the old versions, and it doesn't work very well. There's also no validation. Now you could build this on top, but it's not part of the community and tradition of fits that you are strictly saying what a keyword means and what kind of value you should put in there. So this is how I would grade fits. It does pretty well on some of these things. It does really poorly on some other things. So you start looking at the alternatives and grading it. HDF5 does really well on things like structure, evolution. It's sort of versioned, doesn't have any validation. But it also does really poorly with some of the things that people really like about fits. Like, you can't just open it up in a text editor and figure out what's going on. It's in no way simple. Explaining to someone how to write a fits writer would take weeks rather than minutes, right? XML has a different set of problems. It's very inspectable, it's very comprehensible, there's very rich structure, there's validation, all these nice things, but it really sucks for efficiency. You can't put binary data in there and read it in any sort of fast way. This is kind of the downfall of VO table. ASDIF, not to toot my own horn, but I really think it meets all of these criteria, and of course I selected the criteria, so I would. But hopefully I did a good idea. Okay, I have 30 seconds. This is basically what it is. It's YAML followed by 0 or more binary blocks. There's a file. All of this is online, so you can dig down deeper. We have validation. Everything is versioned. We also add some features we know from fits: compression, checksumming. You can stream data out to disk. Check this out if you want to go do those details in less than 30 seconds. We have a site for the standard. We also have a reference implementation, and we have a conference session. At least it's on the board for this afternoon. Thank you.
it's ready to use.
It might evolve a little, but it's, yeah, there's a library.
Ah, exactly. When the timer goes off, the next speaker on that list, please go up near the front and be ready to switch.
Alright, so I'm going to be talking about Radio Astro tools, which is a suite of tools that were developed based on some ALMA funding. I'll list off a few of what these are, but if you want to see them, this is the website. The group that contributed, at least to the initial, is all listed up here. So Radio Astro Tools is really mostly the Spectral Cube package, which is a toolkit for working with spectral data cubes. So cubes that have 2 spatial dimensions and 1 spectral dimension. And of course we've started this with the nice little logo up there indicating it's ALMA and Python, but this is not actually a purely radio toolkit. It's for working with data cubes in general. The most recent publication to use it was working on optical data, so from Muse data cubes. These are slices from a gigantic optical data cube. What I think is most important for maybe this room, and actually just about the package in general, is that it's a nice place, it's an interchange location. It has great I/O capabilities. So it can read in a CASA image, so this is a radio data cube produced by the CASA package. You can read in FITS cubes as long as they conform to some standard. It can read these LMV cubes, which I hope none of you have heard of. Maybe one person in the room has. I guess I would like to see it read ASDFs if we can get that going later this week. And but then it does a lot of things on the output side. It can send things to YT for visualization and for analysis, to Glue, if you guys have heard of the Glue visualizer. It can send it to DS9, which I guess I don't even have up here. And it can do a lot of these things very efficiently because it uses the memory mapping capabilities of FITS. So the way any given session might look is you can load data, so from Spectral Cube, import Spectral Cube with different underscores and capitalization. Read a file, so in this case I'm reading a CASA image file. And then you can, say, change the spectral units from frequency to velocity, or however you want to do it, and pick your velocity convention, things like that. You can take slices and moments, various convenient things. I think that my usual way of looking at a package is by creating an object and hitting tab at IPython. That's really the only way I ever learn about packages. So here are all the things that it does. I want to highlight the particular features that are probably interesting. So you can apply any function to your cube. Now this is not the cube is not a NumPy array. It does contain one, but in order to keep things efficient, we have different ways of applying things to memory, because if you depending on the order of the data on disk, there are faster approaches for some of these functions. Anyway, that's details. Spectral slab means take a chunk out of the cube. There are various different ways to get subcubes, including using PyRegion or DS9 regions, which I find very useful. You can send it out to various different visualizers. That's in the yellow box over there. And you can do various sort of masking things, and you can copy these cube objects very, very cheaply without copying anything in memory. So you can create as many copies of these as you want, and you're probably going to take up a few more kilobytes, not megabytes. If there are other output files, output formats people want to include, like maybe Jenga or something like that, I would love to work on that this week and see if we can get a few more visualizers out. So one of the other tools that came out of this is the position velocity extractor, which is really a lot of work from Tom. But what it does is, given any data cube, you can draw an arbitrary path along your data cube and get the slice through that. So you can extract a 2D slice along arbitrary coordinates through a 3D cube. Yeah, okay, so this might be useful for the SunPy folks too. The GUI exists in Glue right now, and there's also this independent GUI. And this is an example that for my own data, there's an orbital model, so I sliced through a cube and we came up with a position velocity diagram. It's kind of cool. The last thing from Radio Astro Tools is CASA Python. So can I just get a show of hands? How many of you have used CASA? All right, so there's a decent subset in here. So CASA is the tool for, or it's the package for reducing radio astronomy data, especially interferometer data now. And it's a complete Python stack, but you don't really get access to Python. It's been very hard to install AstroPy into it, things like that. Tom, again, has solved this problem with this package, which allows you to basically use pip or just Python directly to install anything into Casa without hurting the Casa environment in any way. I think that's all I have to show you. So yeah, if you have any further questions, please let me know. But let's try to hack on this later this week if you guys want to add more.
Is detecting it, but there is no comment.
Yeah, I think yeah.
Yes, perfect. Sorry for that. Sorry for that. So, go. So thank you very much for letting me show you a little bit of my baby, as I call it, my first one, and now I have a real one. So this is a software that it started as a small script, and after 5 years it's now becoming something a bit more solid. It's fully written in Python, and it's mainly focused for high energy astrophysics, so X-rays and gamma rays, although it could be applied easily, I think, to other ranges. So basically this is how a pulsar looks like there. The slowdown, actually that's the Vela pulsar, so you can see the two little blimps that corresponds to this. This is called a pulse profile for people who may not know about pulsars, and essentially what it shows is one period or one phase. So normally pulsars have periods of from few milliseconds to a few seconds, and so ideally, so that's one of the things, one of the tools to try to get the period. So it's looking at the pulse profile. Of course, if you don't know the period, you don't know, and it's a brand new pulsar, you don't know how that looks like, so you cannot have a profile or a template and say, well, I'm going to try to fit this. So it's a little more, it takes a little while to get it. So the problem with timing analysis is there's no brand new tool that everybody uses. So, in astrophysics, we tend to use our own software, and everybody tends to write its own software. So the idea of PASS is try to get to the community something reliable, solid, and modern. Right now we have something like that, it's not modern at all, but it's Kronos, it works, but you have your data and you can get three things completely independent. And it's not easy. This is how it looks if you can script it, if you try to do it in a terminal. You need to know careful what this is. You need to know in advance a period. You need to know how the period changes. Then why here you have an indef, which means actually default. I don't know who decided to write it like that. But it's not easy. So the idea was to get, and this is what it does. Because for some reason a trial period or initial period, it calculates the reduced chi-square, and normally in fitting you look for the best fit, so the lowest chi-square. In timing analysis we do the opposite, so a bad period will give you a flat or a uniform pulse profile, so that's a good fit, so you get a low chi-square, and when you find the signal you get a bad fit. So you get your period there. And this is all it does, Kronos. So only one method, which is not the ideal for some of depending on the pulse profile, it might not be ideal. So this is what I came up with, and that's in Python. So you have your data, and yes, you can do different things individually, like you can do in Kronos. Definitely we have different tests for different set of data. But the good thing is that it can do everything for you. If you don't know anything, it just takes your data and goes through it. Of course, it takes time, and we might be talking about a few hours and so on. But it goes through all the data, and at the end, it gives you all the right things, all for you with just introducing your corrected data. I forgot to say that every little point in this light curve is a period that you were trying. there could be around 20,000 periods, and Kronos does this individually one after the other. You might think already of multiprocessing or multi-threading, and to speed up, because each period is completely independent, at the end you want that light curve of reduced chi-square. So this software now uses multi-threading. So if you want 20,000 periods, you just divide it in how many cores or how many threads you want, and it does everything on parallel. As a few samples, for example, this is all done in past, although it's again all Python, and this is letting the software decide what to do. So I had a light curve like this of βx1. It had a beautiful flare here, so we were quite lucky. And I said I want to look at the period, and what past decided it was that there was a solid period, and that would be this line over here with the error. That would be my period for the whole observation. But if you divide it in small slices, you see that the period changes. Here the errors are a little bit overestimated, but I'm finishing now. But you can see that there's something changing. And the other thing that it might also do for you is this nice profiles, energy profiles. So you can see the pulse profile at different times, completely automated, and also by energy. So here you can see the counts and the phase double, just to show you a nice pulse profile. And here you have the same but with energy, so you can see where the emission is actually greater. So in the color scheme you would have brightness. So everything is done automatically. You get much more than with the old software, and that's all thanks to Python. So my time is up. So anyway, thanks very much.
There we go. Okay. All right, so I'm going to tell you a little bit about a little package project that started out as a hack just because I was curious if something was possible, and I ended up working on it more than I intended to. So the package is SCP, and the original question was asking is, wouldn't it be nice to use just, sorry, first I should say, who uses a source extractor? Okay. So wouldn't it be nice if you just use part of source extractor without having to run the whole executable? Like, say you just want to use the background subtraction part, or you just want to use the aperture photometry part. It'd be great if you could do this. You could use it to customize your analysis. Say you just use the detection part and then do your own galaxy modeling at the detected positions. It also allows you to increase the clarity of your pipelines. If you've got a pipeline where you're running source extractor multiple times with different config files, it ends up being a pretty big mess. So the idea is source extractor as a library. So what I actually did is I went into the C code of source extractor and basically did all the manipulations necessary to pull out the code and make it available as individual functions that you could call. So it's really a fork of the stable parts of source extractor. It doesn't depend on having source extractor installed. It's roughly as fast as source extractor, which is to say very fast. There's a C and a Python API for it, and the best part of it is that it allows you to avoid writing Sextractor. So this is just a little demo of what it looks like. So there's just a small test image that I have here saved in the data variable, just a NumPy array. So this is important. It just operates in NumPy arrays, nothing to do with fits at all, completely independent. Fits would just be on the input and output side. You can swap out ASDF or whatever. So to measure background, you would do something like this. That gives you this background object, which then you can inspect stuff like the global statistics of the background. And then you can evaluate the background like this. And so you plot it, you see it's something like this. To subtract the background from the data, this actually modifies the data. Then after subtracting background, you might do object detection. So this is saying, extract objects from data with this threshold, 1.5 times the global RMS. This gives you a NumPy record array, or a structured array rather. So this is how you would get like the X and Y positions of the 30th object. These are all the fields in the structured array. So it's like positions and basic measurements, shape measurements. Here's an example of doing aperture photometry with radius 3 pixels, circular aperture, and a background annulus between 5 and 8 pixels. And that gives you flux error, and some flags. So this is all pretty low level. It's just NumPy. It's something that you could build something else on top of. It could go into default utils. There is documentation on Read the Docs, SCP. And also, one other thing to mention is that the code is really pretty simple. It's just a bunch of C that only depends on the C standard library, and the entire Python wrapper is in this one file, which is a Python file. And let's see, one last thing. I have this up somewhere. Yeah. Well, the other thing is that it's very fast. Running like on a 2K by 4K image takes like less than a second, and the background subtract is like 0.2 seconds or something. There's some benchmarks in comparison to default utils, and it's in the cases where they, like in background subtraction, SCP is like 40 times faster. So it's pretty significant. Yeah, that's it. Thanks. The license on it, so the source extractor license is GPL, but I asked the manual about it, and he said it could be all GPL for this.
Ah, great.
Yeah.
Hi everybody, I'm Kelle Cruz. I wear lots of hats. So what I want to tell you about today is a consulting business which I've started. So this was an idea which came up actually at the Hack Day at AAS in January, and very similar to the Astro Better blog, which was like I got the idea one day and then I just like didn't sleep the next night, and then there was a blog the next day. Science Better Consulting came into fruition in a very similar way, in which it was an idea in January, and I guess it's April. And since then, I've taken a business class. I've incorporated as an LLC in New York, and I just got my the federal number so that I can earn money like 2 weeks ago. So it's gone really fast. I'm really excited about it, and it came from, so I think also a lot of you know that the Sloan Foundation gave me a grant to try to figure out the sustainability method for the Astro Better blog. Because it was just me, on the side. There was no funding mechanism for it, but it takes a lot of work. And so trying to think about how we can, there's a word for this, not profitability, but the revenue generation model, right? Monetize. Although I don't really want to monetize it, right? I don't necessarily want to make it profitable. I just want to make it sustain itself. And so the goals of Astro Better are all of these things, right? Some of the things which we would like to do better, right? We want to, and so the Astro Better blog is not about science results, right? It's about doing science and all of the ways in which we would like to be able to do science better, right? It's methodology, it's practice. And so in some ways the blog is great, right? Because it just puts a post like, if you wanted to do this better, here are the ways which you could do it, or I figured out how to do this, and here's a wiki which we can share those ideas. Wouldn't it be awesome, however, if you could bring someone in or consult with someone who's an expert on one of these things, and instead of having to learn to do it yourself, or instead of having to get a graduate student who's going to spend 2 years trying to figure out this new expertise. And so the idea behind the consulting business, what's my next slide, is that, so we have all of these, and this is just a sampling, right? We could all come up with other things which we wish, which like tools in our toolbox, which we wish we had, but sorry, it's a theme, right? But we really can't be the expert in all of the things, and we can't be expected to be, even though we would really like to do high quality science. So Science Better Consulting is a company which provides a way for individuals to get compensated for applying their skills to a variety of scientific projects. So a lot of us have, so I end up, for example, consulting with the American Astronomy. I don't get paid to do it, I just end up consulting with them, to try to figure out how they can be better communicating with their membership. A lot of y'all, I'm sure, are essentially consulting with other projects. You may not even get co-authorship on anything, right? But you're providing a whole bunch of consulting services to projects. And wouldn't it be awesome if there was a mechanism for you to actually get compensated monetarily for that service? So the consulting business is also a way for people who are maybe more isolated, who don't realize that there's all this expertise exists within the community, to provide access to that expertise to people who may not know that it exists. So it's a twofold thing, which is that it provides the infrastructure for money to flow between people, but it also essentially is a matchmaking service to match projects with expertise. So I'm gonna throw this up there pretty quickly. I want to take away a lot of the administrative tasks, right? Because hiring people is a pain, doing the vendor contracts is a pain. Y'all don't need to know how to do that. So I kind of want to take that away so that y'all can just concentrate on whatever expertise, right? Apparently, this is an expertise of mine, so I'm going to try to do that. And so that y'all can do the stats, y'all can do the programming, graduate students can make web pages, right? Y'all can do the things. One of the things I want to say is that one of the guiding principles, there's lots of guiding principles behind the idea, but one of them is that keeping the expertise in the family. So the analogy that I use a lot is that instead of graduate students going off and getting extra money by tutoring, wouldn't it be awesome if graduate students could make extra money by converting some IDL code to Python for someone? It doesn't even have to be local to them, or for building a research page for a professor who doesn't want to make them themselves. Let's see. So here are the things I'm working. Actually, what I want to do, like in the back of the room this week, is work on the webpage. So don't touch it too much. I just got it up. But the Twitter exists, and I think from this particular audience, well, there's a couple things. One is that right now I can only hire U.S. citizens, right? So that's that's a thing. I would say that that's a growth prospect for maybe 3 to 5 years. Having a London branch, having an EU branch, if that's something which you're interested in, now is kind of the time to start thinking about that. If you wanted to start your own business and kind of, get in on this. But if you are a U.S. citizen and interested in legal to work in the U.S., get in touch, because then I can start listing people. I want to start listing people as potential consultants. I could start that this week. Right. Thank you.
It's going to take a while.
Okay.
Yes, but it's not showing my window.
Oh, you might have to target the cross to the other desktop maybe?
Yeah. Okay.
Is that right?
Okay. This could be interesting because I can't see it here.
You have to clone the... Yeah, right.
Okay, so I'm going to attempt to introduce 2 software projects I'm involved with. These are just, so I'll talk fast, tools for making some analysis and analyzing data, looking at data easier. First one is a tool for simulating and scattered light images from circumstellar disks and comparing it directly to your data. So this is a monochromatic model, just does one wavelength, Monte-Carlo model, and this is the key and it has a nice GUI to wrap around it, so you don't have to play with the interior of the code. So the key here is you can set up a grid of models. You can vary the scale height of the disk, the flaring of the disk, and the density of the disk. You can also set the inner and outer radius, choose your dust model, hit run simulations, and it will run your grid of models. And it's fast. You're looking at less than a minute for a decent signal to noise for a disk model. So once you do that, you can load up the second part of the tool, which is the image viewer. So you load your grid of models, and you can, but you can scroll through different inclinations of the disk. You can scroll through your different model parameters, and you can do this while showing your data in contour over the models. So it's designed to be easy to use. You load up your data. The models are designed to work with the pixel scale of your observations. Scroll through, you can look at different polarizations, polarized intensity, Stokes vectors. You can look at the density distribution. You can look at radial profiles, comparing to it. There's all sorts of tools to change colors and so on. And you can save the individual models as FITS files. You can print the images. So this is good. You can use it in conjunction with other grid modeling tools like SED modeling. They're degenerate, but in different ways. You can use it as a pre-filter before doing computationally expensive radiative transfer code. And it's really good for students. Let them play with this, and they can build up intuition of what scattered light images look like if you tilt the disk, if you make the disk puffier, if you change the dust model. So this is a full release. You can download it, you can use it. It's a mix of C and Python. So the wrapper is Python, the simulation code is C. We've got some papers published that have used this. Now the second tool, this is a newer one. Interesting. This is, so if you work with photometric catalog data, one of the things everyone wants to do with photometric catalogs is look at color, and color magnitude diagrams. And every time you get a new catalog or a new set of data, you read it into Python or IDL, and you plot a bunch of codes, and it's, everyone does it, and it's a little bit, kludgy. You keep doing it. So what I did was I wrote this is just a simple tool that lets you can read in your catalog. It's compatible with the Infrared Science Archive Gator format and with Sloan Digital Sky Survey products, at least some of them. You can load in your catalog. You can compare plots, plot multiple catalogs. You can do color magnitude and color diagrams for any combination of filters that are in the file. You can overplot your extinction vector. You can show uncertainties. And if you click on an individual point, you can plot the SED from the, this isn't showing very well, but it plots the SED from the catalog. So you can look at, that's an interesting point in the color diagram. It tells you what source it is and shows you the SED. This doesn't do band merging. If you have two catalogs at different wavelengths, it won't combine them. That's a completely different and very difficult problem in general. You can also overplot user-provided curves. If you want to plot isochrones or your evolutionary tracks or your main sequence, you can load those in the same format you do. There's a general text format for the catalog. So the idea is that you can use this just to play with your data. It's got a lot of the standard filters are built in, so it will convert flux to magnitude. If it doesn't include one of them, it's user extendable. You can add whatever weird filter you're using, and then you can convert between the magnitudes and fluxes for the different diagrams. And for instance, color magnitude diagram, you can do that. And you can scale different catalogs for a similar common distance. If you're looking at, say, clusters of galaxies or something like that. for the color magnitude diagram. So if you're interested in either of these pieces of software, you can talk to me. I can tell you how to get it, more details if you want. So.
Don't forget your.
Thank you.
Dick swap.
Cool. Okay, so I just wanted to give a quick, rant about code style, but also I think a cool example of, a lot of why PyCharm is cool.
Can you make the font slightly bigger?
Yeah, that's one of the cool things. So it has a presentation mode. Toggle that. Now we're going to presentation mode. Okay. Hopefully that's a little better. Anyway, so it's a live code exercise, so let's make an array. And then let's reshape that to, say, 4x5. Okay, and so you may have noticed there's some cool auto-completion stuff. It understands that reshape is a method on the NumPy array, etc. Okay, so let's say that we wanted to iterate through these elements. The sort of classical way to do this would be thanks. Okay, or J in X range, shape 1. Okay, whatever. So which of I and J is the row and which of I and J is the column? This is a problem that always comes up. So if you use Python a lot of NumPy arrays, then you know this already. But suppose that you're a first-time Python user with only Fortran experience, or maybe it's 3 a.m., or maybe you've had a couple drinks, and now you want to know which is the row and which is the column. So there's a really easy fix for this. You just name them row and col instead of I and J. So this is not something new. This is something that people who code a lot have sort of talked about a lot in the past. It's called sort of semantic variable naming or things like this. Even in the really simple cases, you can do it. So, for example, here, for sample in X range 20,000 instead of for I in X range 20,000. So here's another common one. So everybody knows what C is, right? But what units is this in? Yeah. So you can use AstroPy, of course, for this. So let's say that I wanted to make it. This is C in angstroms per second. But this is kind of funny, like why is this yellow thing here? We can check the doc string for this, and it turns out that this is really small and you can't read it. But it tells us that the actual argument name is not units, but unit. So yeah, I can fix that. And then, the color's gone away. That's cool. Okay, so great. Now C is in angstroms per second, and we know that. Then we code some. Now what unit is C in? And the declaration was way up there where we said it was in angstroms per second, and we want to use it for C over H naught or something like this. And of course, there's a really simple solution to this, and that's to not name it C, but something like C angstroms per second or C ang sec if you absolutely have to. And the fact that these aren't really short variable names is totally okay if you have an editor like this that has nice code completion. So this isn't a new idea in code, like I mentioned, but sort of kind of take this idea further. So I wrote a blog post about this a couple of years ago. So this is, if you're using so this is a 2D heat equation. If you're using finite difference method to basically solve this numerically, the second equation is basically what you'll see in most textbooks, and it's like, okay, there's all these i's and j's and n's, and what do those mean? I don't even know. And I think that there are maybe better ways to even use semantic variable naming, like in mathematical equations and things like this. So the bottom one there is telling you that it's like, okay, we have some point P, and we're looking at the the cells neighboring to it, the left, the above and below, and we're looking at 2 different time steps, the time step now and then the next time step. So, maybe there are better ways to present this so that there aren't just I's and J's and A's jumping around everywhere. And yeah, that's pretty much it. Thanks.
Very quickly. For PyCharm, for the AstroPy community, I've been organizing for the last few years PyCharm licenses, and if anyone wants a PyCharm license, then please put yourself in the Google Docs, because I don't want to spread it on the mailing list, because they make money with this, and I think it will be unfair.
Yeah, there's a link up on the whiteboard where the talk sign up is.
Speaking of the whiteboard, don't forget to